Okay, very good afternoon, one and all. In the last class, we discussed the concept of linear block codes, the matrix description, as well as some of the problems we discussed. And coming to the syndrome decoding, I wanted to tell you one model of problem. And then we can go through the second module, that's regarding the cyclic codes. Here you can see for a 6,3 code. Okay, so for a 6,3, you can see that for 6,3 you can mention it as n comma k. So equate it to n comma k, so that here you have k will be 3. So number of message bits will be 3 and the number of bits in the code word is 6. Okay, so that's where if you observe the received code vector, it has 6 bits. So for a 6,3 code, you will have 6 bits available in the received code vector. Okay, and h is given to you. What is h? I told you in the last class, it is parity check bit matrix. It is of size r by n. So what is r here? 6 minus 3. So r is the number of check bits, which is 6 minus 3. So 3 by n is 6 here. So if you observe the H matrix, it is of size 3 rows and 6 columns. So this is P transpose followed by I 3 by 3. So this matrix is P transpose followed by I 3 by 3. Now here you are given with received code vector. And what you have to calculate? Determine whether the received code vector consists of an error or not. So already I told you to prove that there exists some error. Okay, so y into h transpose should not be equal to 0. If it is 0, then there is no error. Already I told you as a second property of syndrome decoder that first property is x into h transpose is 0. And second property is y into h transpose is 0. If it is 0, then there is no error. And if it is not 0, then there exists an error and cheppam. Okay, so y into h transpose, if it is 0, there won't be any error. Okay, so y is 1000101. So multiply that with the h transpose. So y into h transpose. So you will get, so if you multiply, then you will get a matrix of size 1 by 3. Okay, so already I told you how to multiply. This row should be multiplied with first column to get the first element of syndrome S, because syndrome S is y into H transpose, and second row, this row is multiplied with second column to get the second element, and this row is multiplied with the third column to get the third element. And how you need to multiply? Just 1 into 1. So it will be 1 XOR 1 into 0, that is 0 XOR 0 into 0. So 0 XOR 0 into 1, that is 0, and 0 into 0, that is 0, and 1 into 1 XOR 1 into 1, that is 1. So finally you will get 1, 4 zeros XOR 1. So 1 XOR 1 will be 0 because it has even number of 1s. So like that we will calculate the syndrome by taking y into h transpose. Now finally we obtained it as 0 0 0. Then what you can say here? If y into h transpose is 0, then we can say that there won't be any error. So syndrome is also 0. So there is no error. So it is, you can say that it is error-free transmission. So how can you solve this kind of problems? Just take, here they have asked you to check whether there exists any error or not. So in order to check this kind of problems, just take the product of y into h transpose. How can you get h transpose from h? First, rows and columns must be interchanged. So y into h transpose, if you take C, you will get it as 0. So you can say that it is error-free transmission. Okay. So this model of problems are important. And here another model is for a code vector. For a code vector, what is x generally? X is a transmitted code vector. 0, 111, 000. So X is given here, but in the last problem, Y is given you. So because Y is given, Y into H transpose is our syndrome. Okay, but in this problem, they asked you to prove that X into H transpose is 0. What is this property? This property is the property 1 of syndrome decoder, first property of syndrome decoder. They asked you to just prove that X into H transpose is 0. So you are given with H. So apply the transpose for this so that the rows will become rows and columns gets interchanged. Okay, so prove that X into H transpose is 0. Okay, so for a code vector X and a parity check matrix H given to you, and just get the H transpose. So it will be of size 7 by 3 because 3 by 7 is the original H matrix size. So if you apply the H transpose, then the rows and columns will be interchanged and the matrix size will be 7 by 3. Now X into H transpose is, take the same X code vector multiplied by H transpose. And instead of normal addition, you should take the modulo 2 addition, that is XOR operation. So finally you will get even number of ones during this operation. So here 1 into 1 you have 1, and here also 1 into 1, and remaining all are zeros. So 1 XOR 1 remaining all zeros gives you 0. And similarly if you observe the second column, so here 3 ones, so 1 0 1 in the second, third, fourth positions. So second, third, fourth positions you have only 2 ones. So 2 ones and automatically output will be 0. And in the multiply the row with the third column. If you multiply that in this X you have 3 ones in the second, third, fourth locations. So if you multiply here only 2, 3, 4 locations are 0, 1, 1. So 1 XOR 1 in the third and fourth positions and remaining all zeros. So finally you will get the output as the 0. Okay. So X into H transpose is 0. So that is the first property of syndrome decoder. Okay, this type of model problems you will get in the examinations. Okay, this is all about the first module, and you will have so many problems. You can go through the PDF given to you. So ekkadichharante after cyclic codes you can see. So after the concept of cyclic codes, I have mentioned various model problems. You can check that. Please see the PDF in the available in the Teams. You can see here. After cyclic redundancy check, I have given some of the problems. Some of the problems related to linear block codes. From here, you can see. After completion of BCH codes, Bose, Chowdhury and Hockingham codes, I have given a few more examples related to the first module. You can see the PDF. That is the page 23. So for a 6,3 code, the parity check bit matrix is given. Determine whether the received code vector consists of error or not. So received code vector is given to you. So Y is given to you. So meeku error unda leda ani adugutunnaru. So you need to calculate Y into H transpose. So multiply this with H transpose, and you should take the product. So here you obtained, here also you obtained it as 0. So it doesn't contain any error. So similarly here one more same model problem. Instead of H you are given with G, generator matrix, because it is identity matrix of size 3 by 3, that is K by K, followed by submatrix P. Okay, now using this generator matrix you should be able to calculate the parity check bit matrix H. H calculate cheyali, and H transpose you should get by applying the transpose, and multiply this Y with H transpose. Okay, to evaluate the error. So using this generator matrix, we calculated the submatrix. Okay, because H is P transpose followed by I R by R. For a 6,3 code, R is also 3 and K is also 3. So here identity matrix will come after P transpose. So this is P transpose and this is I R by R. So and H transpose you can write. And here they asked you to calculate or to reconstruct the transmitted code word. So you are given with Y. Okay, Y meeku icharu and error you have to calculate, and Y XOR E will be our reconstructed transmitted code word X. Okay, ikkada meeku Y icharma, and you have to calculate the error E. So because we know that syndrome or error both are equal and it is equal to Y into H transpose. Using that you can calculate the error bit. So error manaki ekkada icharu 110 ochindi. So if you go through the lookup table or H transpose, 110 a position lo undi chudandi. 110 is in the third position. Already I told you. So if you go through H transpose matrix, if you observe the H transpose matrix, whatever the error syndrome, if you obtain it as 1110, it is in the third location. So you will have error in the third bit. So 110, the location of 110 in H transpose is third location. Okay, so third location from MSP. So andukani cheppi ikkada all zeros except third location. So error will be 001000 because third location is the error. Now if you take XOR of Y and E, where E is the syndrome. So based on the syndrome location, we can identify syndrome position, we can identify the error location. Okay, so ikkada maku third location kabatti, and you have mentioned 001 third location from MSP, and all are zeros. Now if you take the XOR of received code vector with the error pattern, that is 001 000, then if you take the XOR of these two, you will get the reconstructed transmitter code word. Okay, so 1 XOR 0 is 0 and 0 XOR 0 is also 0. Sorry, 1 XOR 0, it is odd number of 1, so it is 1. And second position from MSB, so 0 XOR 0, it is 0. And next 0 XOR 1, it will be 1. Next fourth position, 0 XOR 0 is 0. And 1 XOR 0 is 1. And 1 XOR 0 is 1. So finally, we obtain 101011. This is the transmitted code word. Okay, like this you have to calculate. Here you have given with received code word and G matrix. Based on G matrix, you will calculate the H matrix and H transpose will be evaluated. So like this, you can solve this model of problems. Okay, same model of model will be given here, and here also generator matrix is given, and H you have to calculate as P transpose followed by I. In generator matrix, you have I K by K followed by P matrix, and H matrix P transpose followed by I R by R. So you will get H and H transpose, Y into H transpose evaluate chestaru. So error is in the third bit. So third bit ante ikkada 101 annaru. So 101 ante it is in the third position. So out of 7 bits, third bit is the error from MSB. So 001, 0 all zeros. Ante instead of in the received code word 41010, if you have error is in the third bit. Error is in the third bit. If you take the XOR of these two, here error is not in the fourth bit, it is in the third bit. So instead of 1, you will get 0. Here the student has mentioned as in the fourth bit, but error is in the third bit. So ikkada underline cheskondi meeru. Okay, so 11011010. So that's why X is Y XOR E. Like that, almost you have same model of problems. So you will be given with Y, H or clue for calculating H ante G ivvachu, H calculate cheyali. And you need to calculate the transmitted code word X. X is Y XOR E. How can you get E? E is Y into H transpose. Observe the value and observe the position of E in the H transpose lookup table. So 100, ఇక్కడ మీకు 100 ఎక్కడుంది? It is in the 5th position. So 5th bit error. So 1, 2, 3, 4, 5. 5th position, instead of 0, you will get 1. So the same I mentioned here. Okay. So like that, almost all same problems. But the thing is that you should remember S or error. Both are equal to Y into H transpose. Okay. So go through this kind of problems. So almost all the problems are of same model. Okay. So say based on syndrome decoding, the model of problems are almost all similar. So go through that. Now let us move into the cyclic codes. In the cyclic codes, that is a module 2. Okay. In the cyclic codes, here you should go through the encoding process and the syndrome decoding. And here also we have the general matrix representation, or you can say the encoding process of cyclic code. And the second thing is syndrome decoding of cyclic code. The same what we studied in the linear block code. So మన linear block codes లో ఏంటి చదువుకున్నారు? Linear like matrix representation of linear block codes, where you studied that there are two matrices, generator matrix G and parity checkbit matrix H. So we knowing one matrix, you can calculate the other. So and next ఏం చదువుకున్నారు? Syndrome decoding. So 3 properties చదువుకున్నారు. X into H transpose is 0, and if Y into H transpose is 0, then there is no error. If Y into H transpose is not 0, then it is called as syndrome. Okay. And the reconstructed code word X is Y XOR E. Okay. So in the same model, here also we will study the basic cyclic code like representation, encoding process, and syndrome decoding process. Okay. Now let us move into the cyclic code. What is the cyclic code? So the name implies that it obeys cyclic property. And because it is a type of linear block code, please listen carefully. Cyclic code is a subtype of linear block codes. Cyclic code is a subtype of linear block codes. It obeys the following properties. Okay, first property is linearity property. It is same as that of linear block code. In the linear block code also obeys the linearity property. So what is a linearity property? Modulo 2 addition of any 2 code words is equal to the third code word in the same sequence. Modulo 2 addition of any 2 code words is equal to the third code word in the same sequence. Okay. So what you can say here? This first property is same as that of the linear block code. Okay. Modulo 2 addition of any 2 code words is equal to the third code word in the same sequence. And the second property is cyclic property. Please remember that first property is same as that of linear block code. Okay. Now, so instead of normal addition, here we'll follow the modulo 2 addition of any 2 code words is equal to the third code word. And second property that it obey is cyclic property. What is a cyclic property? So cyclic and rotation. So if you rotate by n number of bits, you will get the original bit order. Okay, let us see how it will be. So in the cyclic property, if there is any shift in the code word, that may be either left shift or right shift, it results in the generation of another code word. So what is cyclic property? If there is any shift in the code word, that may be either the left shift or right shift, single bit left shift or single bit right shift, then it results in the generation of another code word in the same sequence. So if once the data is encoded as a code word sequence, or a sequence consisting of code words. First property is modulo 2 addition of any two code words. What is the code word length? N. Each code word length is N. So modulo 2 addition of any two code words is equal to the third code word in the same sequence. That is the first property, linearity property. And second property is cyclic property. Madi, if there is any shift in the code word, so single bit shift, right shift or left shift or single bit or double bit or n number of bits, it results in the generation of another code word. It results in the generation of another code word. Let us see how it will be. For example, instead of single shift, for example, if there are n number of shifts, so n number of shifts, manam oka code word teeskoni daniki n number of shifts cheste, then you will get the same code word. Okay, that is a cyclic property. If there is any shift in the code word, either left shift or right shift, it results in the generation of another code word. Let us see in detail. Let the code word be capital X. Let the code word be capital X. Let the code word X, N, consist of the following bit order as X0, X1, X2 up to so on Xn minus 1. For example, the code word Xn consists of the bits that range from 0 to n minus 1. X0, X1, X2 up to so on Xn minus 1. Let us take that this is the original order of the first code word. Okay, sequence consists of multiple number of code words. Okay, and here we are considering that the code word consists of n number of bits. And what is the code word polynomial when it consists of these corresponding bits? The code word polynomial of X, code word X, consisting of bits in the order X0, X1, X2, X3 up to so on Xn minus 1 is X0 into p power 0 plus X1 into p power 1 plus what is X0 actually? X0 is the LSB bit and Xn minus 1 is the MSB bit. Please remember that here X0 is the LSB bit and Xn minus 1 is the MSB bit. In the examinations, a polynomial will be given as some x, for example, like 1 into p power n plus 3p cube plus some 2p square plus some p plus 1. So like that it will be given, not in the reverse order. So here x0 is the LSB bit and Xn minus 1 is the MSB bit. Please remember that X0 is the LSB and Xn minus 1 is the MSB bit. So X of P is X0 plus X1 p power 1. Here actually X0 into p power 0, but p power 0 is 1 plus X1 p power 1 plus X2 into p square plus up to so on plus Xn minus 1 into p power n minus 1. Okay, this is the code word polynomial if the bit order is X0 to Xn minus 1. For example, if you undergo one single bit right shift, one bit right shift to the corresponding code word, then the corresponding code word consists of bit order as single bit right shift. So this Xn minus 1 will come first, followed by X0, X1, X2, X3 up to so on Xn minus 2. Because one bit right shift, I am telling you to apply single bit right shift to the corresponding order. Then this Xn minus 1 will come first. So Xn minus 1 will be the LSB bit x0, x1, x2 up to so on, and last bit will be xn minus 2. Okay, then the 1 bit right shifted code word polynomial will be here. Instead of sequence, please write it as polynomial. Okay, what is this? If you undergo single bit right shift, then the order will be this n minus 1 will come first and all the remaining will be followed. So x0, x1 up to so on, xn minus 2. And MSB bit will be xn minus 2. Now, 1 bit right shifted code word polynomial will be x dash p. Here dash represents 1 bit right shift. So that will be xn, because this becomes the LSB bit. So xn minus 1 into p power 0 plus x0 into p power 1 plus x1 into p square plus x2 into p cube plus so on plus xn minus 2 into p power n minus 1. Okay, so this is the 1 bit right shifted code word polynomial. For example, if you undergo 2 bit right shifts, okay, let us right shift 2 bits. So similarly, 2 bit right shifted code word sequence consists of the bit order as this n minus 2 will come first here. So xn minus 2 comma xn minus 1 comma x0 x1 up to so on, and the MSB bit will be xn minus 3 because 2 bits we have right shifted. Then the 2 bit right shifted code word sequence, this is 2 bit right shifted code word sequence will be x double dash of p. X double dash of p will be xn minus 2 because the LSB bit is xn minus 2 into p power 0 plus xn minus 1 into p power 1 plus x0 into p square plus x1 into p cube plus so on xn minus 3 into p power n minus 1. Okay, this is the 2 bit right shifted code word polynomial. This is 2 bit right shifted code word polynomial. Okay, polynomial will be x double dash of p, which is equal to xn minus 2 plus xn minus 1 into p power 1 plus x0 into p square plus x1 into p cube plus so on xn minus 3 into p power n minus 1. Here remember that xn minus 3 is the MSB bit and xn minus 2 is the LSB bit. Now, if you go like process the same till n number of right shifts, till n bits are right shifted. Once n bits are right shifted, automatically you will get the original order because the code word consists of n number of bits. If you undergo a single shift, xn minus 1 will come as a LSB bit. Similarly, 2 bits, then xn minus 2 will come as a LSB bit. Like that, if you right shift for n number of bits, then you will get the same bit order. That is from x0 to xn minus 1 with x0 as the LSB bit and xn minus 1 as the MSB bit. So as like if you continue the process and if you go on if you go on the bits by n right shifts, okay, then the original bit series can be obtained as x0, x1, x2 up to so on n minus 1 and possess the same polynomial as the original order. That is x0 with the LSB and xn minus 1 as the MSB bit. So x0 plus x1 into p power 1 plus x2 into p square plus so on xn minus 1 into p power n minus 1. Okay, this is the second property. What is the second property? First property is linearity property. It is same as that of linear block code. So if you take the modulo to addition and XOR of any two code words, each having a length of n, it results in the third code word. That is the first property. And second property is cyclic property. So if there is any right shift in the code word, that may be either left shift or right shift, it results in the generation of another code word in the same sequence. So this is a first code word. For example, if you go on for the 1-bit right shift, you will get another code word having this kind of polynomial. And similarly, if you take 2-bit right shifts, then you will get another code word in the same sequence. So like this, if you undergoes n number of right shifts, n bits right shifts, then you will get the original code word polynomial. Okay, so then you can say that it obeys the cyclic property. So two properties of cyclic codes we studied. And third property is multiply x of p with p. X of p with p. And add x dash of p. What is x of p? Code word polynomial of the original order. Original bit order. And what is x dash of p? X dash of p is the code word polynomial for 1-bit right shift. For 1-bit right shift. So p into x of p XOR x dash of p. Let us see what you will get. So take x of p, that is x0 plus x1 p power 1 plus x2 p square plus so on plus xn minus 1 into p power n minus 1. So multiply this input polynomial, code word polynomial with, or you can say original bit order polynomial with p, and take XOR x dash of p. What is x dash of p? Is the 1-bit right shift code word polynomial. Already you obtained 1-bit right shift code word polynomial as xn minus 1 into p power 0 plus x0 into p power 1 plus so on xn minus 2 into p power n minus 1. So the same I have mentioned here. So this is 1-bit right shift code word polynomial. Now let us take the XOR of these two. So p into multiply with p. I told you to multiply it with p. So p into x0 plus x1 into p square you will get plus x2 into p cube you will get plus so on xn minus 1 into p power n minus 1 into p. It will be p power n. Let us take the XOR of this p into x of p with x dash of p. If you take the modulo 2 addition of these two, so here take the p power 1 ekkadekada undo chudandi okasari, p power 1 here you have, and x0 into p. So here x0 into p also represents it is p power 1. Okay. So take p as common. If you take p as common, you will get x0 XOR x0. So for same inputs, XOR operation is 0. So this will become 0, and p square if you take common, you will get x1 XOR x1. And similarly, if you take p cube as common, you will get x2 XOR x2 plus so on plus p power n minus 1. You have the constant as xn minus 2. So xn minus 2, and here also for p power n minus 1 you will get xn minus 2. So xn minus 2 XOR xn minus 2 into p power n minus 1 plus whatever the leftover terms xn minus 1 into p power n plus, and here you have p power 0 value, that is xn minus 1. So the constant of p power 0 is xn minus 1. Now here x0 XOR x0 is 0. So the XOR of the same inputs results in 0. So all these values are 0 except the p power n constant and p power 0 constant. So what is the constant for p power n? Xn minus 1. And what is the constant for p power 0? That is also xn minus 1. So finally, if you take p into x of p plus x dash of p, here plus represents the modulo 2 addition or XOR operation. So you will get xn minus 1 into p power n plus xn minus 1. Okay, so it will be xn minus 1. Take xn minus 1 as common. P power n plus xn minus 1. Okay, so p into x power p XOR x dash of p is xn minus 1 into p power n plus 1. So this is the third property. So third property states that the XOR of 1 bit right shifted code word polynomial with p into original code word polynomial if you take, then you will get it as x of x n minus 1 constant x n minus 1 into, what is this constant actually? This constant is a MSB bit of original code word order, okay, into p power n plus 1. So wherever if you get this kind of value in the LHS value, you can replace it with the RHS part. Okay, so while doing some of the examples, you can find out where you can use this kind of properties. Okay, so we have studied three properties. One is linearity property, and other is cyclic property, and third one is the general property equation where p into x of p XOR x dash of p is xn minus 1 into p power n plus 1. Okay, remember this third relation. Next, now coming to problems. So in this fifth chapter, especially part A, so you will get more like questions will be only related to problem, like it will be only problematic part. Okay, so coming to this module 2, you will have this model of problems, and these are very important. Okay, so I will mention the concepts only in 2 slides. And if you remember these 2 pages, you can do problems based on cyclic codes. So elanti questions ostayante, generate the non-systematic code word for some message bits and cheptaru. So message bits will be given to you and a generator polynomial will be given to you, and you are asked to calculate the code words. And మీరు గుర్తుపెట్టుకోవాల్సింది ఏంటంటే the code words can be generated by using either the non-systematic procedure and systematic procedure. Okay, so this is non-systematic and this is systematic procedure. Okay, so generation of non-systematic code word and generation of code words using systematic procedure. So in general, you will be given with the generator polynomial which is in this form. So so a generator polynomial which is in this form will be given to you in the question, and sometimes message polynomial will be given, or sometimes they did not give in the question. So you will be given with like some 7,4 code. So for 7,4 code, how many message bits are there? Any one of the student please respond. For 7,4 code, how many number of message bits are available? See, I am asking you for 7,4 code. How many message bits are there? Any one of you please respond. For 7,4 code, how many message bits are available? Any one of you please respond. So So almost all 40 students are available. Tell me, for a 7,4 code, how many message bits are available? So how many combinations of message bits you can represent? Anyone from the class? So did any one of you listen the class or not? If so, please respond. So any one of you please respond. For a 7,4 code, how many number of message bits are available? H2, Anushka? H2. C2. C2. H0, Achyut. H0. G1. C9. So no one is following the class. C9. So how many of you know the answer? Please raise your hand at least. For a 7,4 code, how many number of message bits are available? G5. Okay, ma, please tell me. For a 7,4 code, how many number of message bits are there? K. K is? Okay, okay. Okay, actually I'm not able to listen your voice. Okay, you can down your hand. Thank you. Okay, for 7,4 code, here k is 4. Okay, so because k is 4, the number of message bits are, how many combinations will be there? 2 power 4. So that is 16 combinations are available. So 16 combinations are available. So sometimes in your examination, they will be asked to, so you will be asked to calculate the non-systematic code word, or they will ask you to calculate the code word using non-systematic procedure and చెప్పి అడుగుతారు. Okay, so sometimes they will give you the message bits, like they will give you 4 bits 1101 and చెప్పి they will provide you some data like 1101 or 1100, like that they will provide. For example, if they did not provide and they ask you to calculate the code word using non-systematic procedure, so all code words enter. So if you want to calculate all code words for all 16 combinations of message bits, you have to calculate the code word. So 16 combinations and like 00002 to 4 ones, 1111. So up to all those 16 combinations, you have to calculate the code word capital X, which can be obtained as the message polynomial multiplied by generator polynomial. Okay, so m into g. So you will get the code word capital X. Okay, like that you can just by multiplying the message with generator polynomial, you can get the non-systematic code word capital X. Okay, next similarly for generation of systematic code word, we'll have to follow 3 steps. First step is some message polynomial will be given to you and multiply that m of p with p power r. What is r? For 7,4 code, what is r? 7 minus 4, that is 3, at a p cube. So multiply message polynomial with p power p cube. Okay, and divide that with some generator polynomial given in the question. So a generator polynomial of this form will be given in the question. Okay, so p power r into m of p is first step, and divide this with g of p, that is the second step. And once you divide, automatically you will get some remainder. That remainder may be 0 or some value, that is a secondary issue, but you will get some remainder c of p. Okay, so p power r into m of p by g of p. If you divide this with g of p, you will get some quotient plus a remainder divided by g of p. So this remainder here is nothing but the check bit polynomial c of p. Okay, so now please add the remainder c of p. So you will get some remainder. So add that remainder polynomial to the shifted message polynomial to get the code word. Okay, so code word using non-systematic procedure is just multiply the message polynomial with g of p. I will tell you how to represent the message polynomial, and g of p will be given in the question. And for non-system using systematic procedure, it is different. M of p is multiplied by p power r and divide by g of p and divide by g of p. You will get check bit polynomial. Now as a third step, p power r into m of p, that is the first step, you will get shifted message polynomial XOR c of p is our systematic code word. Okay, so anyhow you will be more clear if you do problems. So we'll discuss this model of problems in the next class. Okay, till now we have completed the 3 properties of cyclic codes. One is linearity property, second is cyclic property, and third is a relation p into x of p XOR x dash of p is xn minus 1 into p power n plus 1. And we have seen the procedure for code word generation using non-systematic procedure and systematic procedure. Problems based on these 2 concepts are very important. Okay, We can discuss all these things in the next class.